A Maxwell distribution asks the following question: what is the probability of finding a molecule slash particle in a closed container in perfectly ideal gaseous state traveling in the speed range c to c plus dc. So what we have here now is a closed container, let's say a square container, where there are gas molecules present, and each gas molecule has a particular speed c, maybe c1, maybe c2, this has c2. And what the Maxwell-Boltzmann distribution deals with is Maxwell distribution is dealing with is basically one particular speed c, and it is asking what is the probability that if we pick a molecule, any random molecule from here, that the probability that it will have a speed in the range c to c plus dc. So it will have a speed between c to c plus dc, and this dc is nothing but the range of speeds. There is a range of speed and there is an infinitesimal quantity, right? Before we go on, we should define what we mean by the perfectly ideal gaseous state, and this actually forms a part of the assumptions of the distribution. A perfectly ideal gaseous state is one where the particles are point masses. Particles are mainly point masses and are completely identical to each other. That is, no two molecules are different from each other. They are completely identical molecules, right? Secondly, the motion is completely random. The motion is random. What I mean by random is, we shall define randomness later, but randomness according to us is where the motion of every particle is the motion of molecule, not particle, is equally probable in any direction, in all directions. That is, and this type of situation is called isotropic situation. What I mean is, when there is a particle here, let's say it is traveling with a velocity c, this c actually may be towards any direction. When it is traveling, it is equally probable to travel in any direction. What I mean is, all the directions are equal, and no direction is particularly unique for this particle, right? Thirdly, there is a third assumption which is very important, is that there is no external force field. There is no external force field like gravitation. Gravitation may be completely neglected, or electrostatic forces. in fact there is no attraction and repulsion that exists between the molecules in the perfectly ideal gaseous state. No electrostatic forces. This implies with these three assumptions implies what I said is the most important thing, that the directions are completely independent, or rather the directions are implies that the directions are not different from each other. That is, the directions that the molecule can take are not different from each other. And we may elaborate further to say that this is actually a classical mechanical problem. How to solve this is actually a classical mechanical problem, wherein you must realize that the particle is traveling in a 3D space, and if it is traveling in a 3D space, it obviously has three components of velocity, the x, y, and it is actually traveling in the our famous xyz Cartesian plane, Cartesian system, right? And that thus it has three components of velocity, vx, vy, and vz. And actually this is, so what I mean by that, this is a 3D problem, but we don't need to stress ourselves with the solving of a 3D problem, and this 3D problem can actually be broken down into three 1D problems, and our job becomes as easier. We will see how our job becomes easier because of our assumptions, and we say that all these three directions are independent of each other. These three directions are indeed independent of each other. These are independent of each other. But remember that the randomness or isotropicity does not allow the directions to be different from each other, and this is actually the important point, from each other. Why this is an important point is because that whatever we solve for one dimension will automatically be true for all the other two dimensions, that is all the other two components of velocity. So whatever we solve for Vx will automatically be true for Vy, will automatically be true for Vz, because of our assumption. But again, they are independent of each other, and so we should establish our famous relation, that the relation between C, Vx, Vy and Vz is this, the famous vector resultant equation. And this actually says that the components of velocity are Vx, Vy and Vz, and the net velocity in the 3D plane of the molecule is C. Right? So this is the premise of this derivation. So we start off with an arbitrary component, and my component that I would start off with is Vx. And again we ask the same question: what is the probability of finding a molecule with x component velocity ranging from Vx to Vx plus dVx. So we actually, what we did was we broke down the problem of three dimensions into a single dimension Vx. So we can define the parameters like this, that let dn Vx be the number of molecules. These are variable, the number of molecules in the range, given range, right, in the given range, and the number of total molecules, which is a constant, total number of molecules Pn. And as we know, we are finding a probability for, so finding the probability, we would require the total number of elements in the sample space. So this number of elements in the sample space, it will be our n, right? So our required probability is nothing but dn Vx by n, and what we need to find out is just this dn Vx by n. Now we start off with a safe assumption. The safe assumption is that this dn Vx by n is nothing but proportional to our range of velocities dvx. Why does this assumption somehow seem to work? Is because if we take a large range of velocities, the number of molecules in that range would also be high, and it is often a safe assumption to take up direct proportional relationship. And so this is a part of our, this is another of our assumptions that we take in this derivation. Now if we remove this proportional sign, we should get a function. We should actually replace it with a constant, and in fact this constant is what is a function, and this function is written as f Vx square dvx. What is this f Vx square? This is actually a probability density function called the PDF. We will call it the PDF. Obviously there are few things to notice here, that this Vx, we have taken Vx squared and not the function of Vx. It's Vx only, not Vx but Vx squared. Obviously a function of Vx squared will be a function of Vx also. Then why not Vx? Why not Vx square? Why not Vx but Vx squared? That is a question. Why Vx? So this question can be this question may be answered like this, that Vx is a velocity. Whatever it is a velocity, and there is an equal chance that a molecule may lie in the range v. So let's say this is our origin and this is our velocity. So if it is traveling with Vx and this is dv, this small distance is dvx, we are looking for all the molecules with a velocity Vx plus dvx in between, in this line, in this region AB, right? But what, there is an equal chance that these molecules also lie in the range minus Vx, and this is, let's say, minus dvx, in this range as well. This is a dash b dash, this velocity, right? If we had Vx, the problem, if we would have had f Vx only, right, f Vx only, the system would have a net velocity towards this direction only, towards the positive direction only, right? And this is not the case. Then their system would not have been random. The randomness would have diminished. Randomness would be diminished. This is our assumption, that randomness is not to be diminished, and thus to maintain this symmetry, or rather the randomness of the situation, we actually have to use the f. We have to take the probability density function as f Vx equal to we have to take the probability density function as fvx squared. This can be extended to all the other directions without a change in the functional form. Remember, as this motion is completely isotropic, we can actually say that yes, the functional form remains the same, and whatever happens in one direction is same in other directions as well. So we can write for similar notation that this to be true, and again we can write with again similar notation that this to be true. Now we shall shift our focus to a simpler case of the 3D Maxwellian. So what we were talking about was the problem of the 3D Maxwellian. We should shift our focus to the 2D Maxwellian as well. It's an important part of the problem, that what is the probability? The same question. So we shift our focus to this, that what is the probability of finding a molecule that has simultaneously an X component Vx2 Vx plus dVx and Y component, and this is velocity, Y component velocity as Vy2 Vy plus dVy. We saw what these were in this case, Vx and Vy, and obviously this, as we mentioned before, that the two directions are independent of each other. So it is the rule of probability that for two independent events we have to multiply them. The probabilities have to be multiplied. So the probabilities were multiplied and we get this. We get this form. And this actually is written as dn xy by n. Now we shall go for a definition of a coordinate system, and the same way we define for a 1D system, we will define the 2D coordinate system, the Cartesian coordinate system simply. So we have a wide y and we have an x. This is the origin, and so what we said was, so simultaneously the x component of velocity is vx, and this part is the dvx, and this is the vy, and this is the vy, and this part is the dvy. So this is the vx comma vy, and if we had v x plus dvx comma vx plus dvy, this is the point. This is the vx comma, this b point is the vx, and this a point is the vx. A point is the vx comma vy, and b point is the vx comma dvx, vx plus dvx comma Vx Vy plus dVy. What we are interested here is the number of molecules that fall within this range, right? We are only interested in the number of molecules that lie within this square. This is the number of molecules that we want, right? So let's define something called as, which is another way to say is we basically need the number of gas molecules, which are basically the number of point masses that we want in this region, right? So that is actually from our equation, which is our let's name our equation. This is our equation, let's say 3, right? And we had 2 equations before. Let's name our equations likewise. Let's call this 1. Let's go on and call this 2. Let's go on and call this 3. Oh, then that would make this 4, right? That would make this equation 4. So we define something called as the point density at Vx comma Vy. This is given by point density. This point density was nothing but the density of points in this system, which have the speed range Vx comma Vy, which lie in this speed range Vx plus dVx comma Vy plus dVy. So this is given by dnxy by dVx comma dVy, and this is what we get from our equation 4, right? So this is actually equal to n f Vx square into f Vy square. Right. So this is our point density at Vx plus in this square. So this is the point density at not even Vx plus here. This is actually the point density in the rectangular region. Right. Now what we are going to do is we need to, so the aim of doing all this is somehow we want a functional form of this f. We want an exact functional form of this f. So what we will do now, in the same coordinate system, we shall define another coordinate system. What is the reason? We shall see, but let for now take up coordinate system such that the velocity Vx plus dVx comma Vy plus vdy, let's say we want another coordinate system. This coordinate system will be defined such that the x axis of this component, x axis of this coordinate system should pass through the point Vx plus dVx comma Vy plus dVy. What is the point is that we want to diminish this y component to 0. What is the use of diminishing? That we shall see. That we define this, and the point density, let's call it PD, at Vx dash, and this Vx dash comma Vy dash, right? This Vx dash comma Vy dash is nothing but the velocities in the x and y direction in the new coordinate system. So this coordinate system is the y dash x dash coordinate system, right? So we define it as dn Vx dash into dn Vy dash by dVx dash into dVy dash is equal to n times f Vx dash squared into Vy dash squared. But remember that this is a perfect ideal gaseous system, and the density must be same regardless of the coordinate system that we choose. So clearly we can equate these two things, this 5 and 6, equate 5 and 6, and we should get something like, the n should cancel out, so I am not writing that. So this is f vy vx square, vx squared f vy squared f vx dash squared comma f vy dash squared, right? Now the point was, we have defined the coordinate system such that vy dash is diminished to 0, and what happened was, this, that box, actually somehow that box, not even that box, that vx plus v dvx comma vy plus dvy lay on the x-axis. That point was lying on the x-axis, right? So remember that this point was, this point vx comma vy was actually the resultant of vx and vy, and this was the vx dash, this point was the vx dash in the new coordinate system. In the new coordinate system, vx dash was nothing but the resultant of vx and vy, and we know what is the resultant of two vectors, two mutually perpendicular vectors, is nothing but, let's call that the resultant c1 squared is nothing but vx dash squared plus vy dash squared. Not dashed, sorry, this is an original coordinate system that we used, so this is this, and since we took that to be 0, so the final equation stands out as f vx squared into f vy squared is equal to f of vx squared plus vy squared times f0. This f0 is actually a constant quantity. Let's call f0 equal to a. So f0 was taken to be a, and now what we had to solve was this equation. Not this. Right? This is the functional relation that we get. The functional relation, if you notice properly, is a unique functional relation. This is actually satisfied by only one function in this world, which is actually an exponential function. And if you see by analysis that there are only two exponential functions, let us say there is a positive quantity alpha. Alpha is a positive quantity, right? So there are two equations that may satisfy this equation. F vx is actually a e to the power minus alpha vx squared, and f vx equal to a e to the power alpha vx squared. So we have two equations, two solutions for the given equation. Logically speaking, there is only one, physically and logically there is only one possible solution to the equation. And to explain that situation, to explain that equation, we should realize the physical significance of both these equations. And let's start from obviously the second one. Why I choose the second one is because this is not physically possible. This is not physically possible because what we should explain what happens. So we should write the equation of dn vx by n. This is our equation 1, and this is a alpha vx squared dvx. What is the problem here? What happens if vx tends towards infinity? So if vx tends towards infinity, if vx is tending towards infinity, then dn vx by dn that tends towards infinity. If that is tending towards infinity, this is obviously physical, that is tending towards infinity. And remember that when Vx is tending towards infinity, that the kinetic energy in the x direction tends towards infinity. That means the probability of finding a molecule with infinite kinetic energy, that what is kinetic energy, half m Vx squared, is infinity, which is not possible because firstly the probability of an event cannot tend towards infinity, right? It should lie between 0 and 1. If it is a normalized situation, it should lie between 0 and 1. So this is impossible. The second situation, second equation is impossible. An impossible situation is what this is, what the second situation is. And this is just the reverse with the first case. Now if we put the first case, and we should take it here, what's happening? Okay, let's write it again. dn Vx by n is e to the power minus alpha Vx squared. This is e, there is an a here, and this is dvx. If Vx now tends to infinity, kinetic energy tends to infinity, and the probability that dn Vx by n, if you put infinity in this equation, e to the power minus infinity occurs, a large number, or e to the power large number is 1 by e to the power a large number, and this actually is 0. This tends to 0. This is perfectly fine. This is physically has some significance, and we expect this to happen, that molecules with very high speed should be comparatively less. This is what we expect. This is completely fine physically, and we have our functional form of the equation. This is f Vx equal to a e to the power minus alpha Vx square. This is completely fine, and we have a form of our functional form of our probability density function, which is a great news.